Hello, and welcome to your Generalized Linear Models 2 lecture. So previously, we've been establishing that we can take the linear model and we can extend it so that it can apply to a ton of different scenarios, not just the typical ones that we would normally think of. So today in this video, we're going to talk a little bit about further, maybe less common extensions to the generalized linear model framework that we can make so that we can then in class focus a little bit more on how to actually implement these models. So the first thing we're going to talk about are error models. And this is actually a special case of something that'll be more common as we talk about the Bayesian framework in general, because this tends to be a little more common in Bayesian models than in frequentist models. But error models are basically just the case where instead of just modeling a single thing, right, we're just predicting an outcome. In this framework, we can basically take any parameter in the model. So maybe not just the expected value, but also the variance of our data. And we can use those, or we can predict those using different predictors or covariates in our model. For example, in a regular linear regression, sort of the baseline for everything we've been doing, we know that what we're actually modeling is the expected value, usually what we think of as like our best guess or the prediction for the model. But there's another parameter that we sort of don't really talk about a lot. I mean, I guess we talk about it when it comes to like the assumption of homoscedasticity, but we have this other parameter, the variance of your responses, that we essentially ignore. We let the model fit it, but we're not really thinking about it. However, there's nothing saying that we can't also model this parameter. Normally we're modeling the expected value, but we can also model the variance. For instance, think of this scenario. Imagine that we're doing an experiment in which people are supposed to memorize a bunch of lists of words and they're supposed to then like remember those words later on. Let's say one group of these people is told that they're going to place bets between 0 and 10 points on whether they're going to remember the word, and their goal is to maximize their score, right? They get the number of points they bet if they remember it. They don't get it if they don't remember it. And the other group is doing the same task, but when they're asked for their ratings or their scores, they're just told to give a rating on a scale of 0 to 10 on how likely it is that they are going to remember each word, 0 being like, definitely not going to remember this, 10 being like, definitely going to remember this. And their goal is to accurately assess how they're going to perform in the future. Now, when we look at the scores, right, everyone's giving us answers on a scale of 0 to 10. We might not only expect differences in the expected value or the mean of the different groups, we might also expect that the answers we get from each group are also going to differ in the variance of their answers. And this is actually something I found in my research way back in grad school. We did this very experiment, and we saw that people who were told to bet on their words actually use the extremes of the scale far more often than those who were told, oh, just give us a rating of how likely it is to that you're going to remember this word later on. And this is really important because if you're just looking for differences in the mean, you might miss really important patterns and you might not model it correctly. And so having models where we can do things like model the variance based on which group you're in, the bet framework or the rating framework, is going to allow you to capture this phenomenon better. And apart from answering research questions we might want to answer, it's really important that if we do really think that the variance of responses might actually depend on something like what group you're in, then we need to account for that in our model. Because remember, our model is making the assumption of homoscedasticity, that we have this constant variance. And if that's not true, we probably should account for that in our model. By default, most regression models, like the linear regression, assume that variance is constant, but we can get around that by actually modeling the variance according to a bunch of different predictors. Now, one thing to remember is that in GLMs, most assumptions we make are about the residuals or the errors of the model. So essentially, we're saying, hey, we know there's no homoscedasticity. Different groups have actual different variances within their group. But if we actually incorporate that into the model, then we no longer have the issues that we would normally have from violating that assumption. Okay, so let's look at a really simple hypothetical linear regression. Now, one thing that we're really used to doing is modeling the expected value, right? In a linear regression, typically we have a Gaussian likelihood. So we're essentially saying that the expected value is going to be normally distributed around our predicted value, which of course we just get by taking our coefficients, multiplying them by our predictors with some variance. Now, the difference here is that we're now adding basically like a submodel to our model, which allows us to model that variance according to a different or the same set of predictors. Now, you might notice that I've called this X prime and beta prime. That's because we don't necessarily have to have the same design matrix or the same coefficients as in the actual typical part of the linear regression. We can use different predictors, and of course that will come with different coefficients. So we can, but don't have to have those be the same design matrices. Now, of course, this is a more complicated model and is a little bit more difficult to fit, but it can be a really powerful tool if we actually think that there are predictors we have in our data set that may change the variance of the residuals in our model. Now, again, even though this seems like a completely new thing, all we're doing is extending what we've already been doing, which is basically we're modeling a single parameter, the expected value, and now we're saying, hey, there's other parameters in the model. Let's model those as well. So we can model the expected value, the variance, and if there's any other parameters in the model, we could probably model those too. The next extension that we're going to talk about are mixture models. Now, mixture models assume that data comes from multiple distributions in various proportions. So essentially what we're saying is the population of data we see is actually a mixture of multiple subpopulations. Here's kind of a picture of what that might look like. So here we have distribution A in yellow and distribution B in this burnt orange. And then the dotted line shows us a mixture of those two distributions. Here's a more specific example. So let's say we're looking at the amount of money that people spend on fast food. Well, let's say that there's two kind of categories of people on how they spend on fast food. There's people that spend a lot, but it's more varied, so like this distribution, and there's people that spend a little bit less, they're a bit more consistent. Now, if we were just looking at like a sample of people and how much money they spend on fast food, we would see a mixture of these two distributions, like the dotted line. Or we might see something like if we have two sexes of penguins, then we might have, males distributed one way, females distributed the other way. And so the actual distribution of the heights of the penguins would be a mixture of the two male and female distributions. For those of you that have taken some kind of data science class that talked about clustering, Gaussian mixture models are mixture models, as the name implies, that we use for clustering. Essentially, we're assuming that all of these populations are a bunch of different normal distributions mixed together, each distribution being a cluster. But we can also apply this to a generalized linear model framework. One really common example of a mixture model in the GLM framework is 0-1 inflated beta regression, or ZOIB for short. So if you remember, we talked about beta regression, which is good for modeling values that are between 0 and 1, so probabilities, proportions, stuff like that. However, as we talked about, one of the limitations of beta regression is that you can't model exact zeros or ones. It basically assumes that everything is between 0 and 1, non-inclusive. So we could actually use a mixture model to help overcome this problem. Essentially what we're saying is that the data that we observe comes from a mixture model with three components: a component of zeros, a component of ones, and a component of things that are between 0 and 1. So ZOIB is really just three regression models, aka a mixture model, in a trench code. So the first is a model that is a logistic regression that basically just predicts, is a value, like an outcome that we have, going to be an extreme value, so a 0 or 1, or is it going to be between 0 and 1? So we're making that dichotomization first. Then, for data that we've decided is extreme, so it's either a 0 or a 1, we have a second logistic regression that decides whether it's a 0 or a 1. Lastly, for those values that we predicted are actually between 0 and 1, we run a very typical beta regression that predicts those outcomes between 0 and 1. So essentially, we have these 3 regression models that we're fitting. Let's start with this top one here. This is the one that I've outlined that basically predicts 4 values between 0 and 1, what the value is going to be. And what we're going to do is just a beta regression. So we're going to take a design matrix of our choice and multiply it by the coefficients that we fit for the model. Then we have 2 other regressions to fit simultaneously. First is the one you can see here in the middle that basically tells us, is the value extreme or not? Is it a 0 or 1? Or is it between a 0 or 1? Then we have the second logistic regression, which 4 values that we've already designated as extreme decides if they're a 0 or a 1. Now notice, we could put the same predictors, or at least there could be an overlap in the predictors of the design matrices of all 3 of these models. However, these coefficients aren't fit with each other in mind. What does that mean? Basically, what that means is that the betas here don't really interact with each other. I guess they're not completely dependent in the sense that like these models are connected, right? First, we decide if something's extreme, and then depending on what we decided there, we put it into one of these other 2 models. However, this can cause some issues because if we have the same values in the design matrix, right, the same predictors, maybe it's height or weight or age, they might have really counterintuitive effects. For instance, I want you to do a little bit of a thought experiment. What if our model was trying to use income to predict something, and it said that higher incomes made you more likely to be a 1, right, an extreme value? But for values between 0 and 1, higher income actually reduced your prediction. It made it so that our predicted value was closer to 0. What you have to do when you're thinking about 0-1 inflated beta regression is figure out if that makes sense. We basically have these completely separate processes, right? A process to decide if you're extreme, a process for extreme values to decide if you're a 0 or a 1, and a process for the continuous between 0 and 1 values to decide where you are in that spectrum. And because all of the effects that we can get from those 3 different models don't talk to each other, we need to make sure that that makes sense with the process that we're working with. For instance, let's say we're modeling the proportion of items you got correct on a spelling test. If higher income means you're more likely to get 100%, would it then make sense that if you're between a 0% and 100%, that higher income actually makes you have a lower spelling score? In that case, probably not. And so in that case, we might not want to use 0-1 inflated beta regression. Another extension we can make is to have latent variable models. A really common one is the cumulative logit regression. Now, cumulative logit regression is one example of an ordinal regression model. Remember, ordinal data has discrete choices. So you don't have a continuous value, but you do have a very specific order to the categories that you can have. So an example of non-ordinal categorical data would be like your favorite color. There's not really a meaningful order that we can say, okay, red is at the bottom of the scale and blue is at the top. Whereas if we have something like a Likert scale, like that goes from strongly disagree to strongly agree, that has discrete choices, right? You only have 5 categories that you can choose from. But there is a very clear order there that might be important for us to take into account. Now, when we have ordinal data, if we don't know about ordinal methods, we might be tempted to either go in one extreme or the other. We could either treat it as categorical data and lose all of the really important information that comes from the order of the categories, or we could go the opposite direction and treat ordinal data as a continuous value, in which case we're completely ignoring that people have to choose a discrete category. It's not a continuous value. So if you don't want to do either of those things, one thing you might want to do is appropriately treat the ordinal data as ordinal data. And there's actually a ton of different ways that you can do this, but one really common one is cumulative logit regression. So cumulative logit regression assumes that there's a latent continuous trait that causes your discrete responses. So let's say for a Likert scale, then we assume that there is some continuous variable called agreement, which is kind of the underlying process that causes you to have one of the various Likert scale responses from strongly disagree to strongly agree. In a cumulative logit regression, we assume that the latent trait is modeled as a logistic distribution. It's very similar to a normal distribution, but essentially this is a distribution that we're going to say, okay, agreement is distributed as a logistic distribution. So when we're looking at the impact of various predictors on which response you gave, we are essentially assuming that those predictors move where you are on this continuous latent scale. For instance, if we had age as a predictor, we might say that the older you are, the higher your latent agreement tends to be. But of course, one of the things we have to keep in mind is that we actually are modeling a discrete set of choices, or really an ordinal set of choices. You don't have a continuous response on a Likert scale. You have 5 different responses and you can give whichever one you want. So in addition to modeling this latent agreement variable, we also model cut points. These cut points are thresholds, which basically indicate where in the latent distribution you switch from one category to another. So for instance, here's a figure from a paper I really love about ordinal regression in general, showing the cumulative logit model. And you can see that if your latent agreement is predicted to be anywhere down here, you are going to respond with the lowest category. But as soon as you pass this threshold here, you would give the second to the lowest category, then the third, etc., and etc. So the beautiful thing about cumulative logit regression is that it preserves the importance of the order in the responses, right? We're not throwing that information away and treating these as discrete categories that have no order, but it also respects the discreteness of the actual observed data. If you're responding strongly agree, that's a specific category. It's not a continuous value that you can respond with. Now, something that'll be important in the next section is essentially what we're doing is we're assuming that predictors, or sometimes we call them covariates, have this kind of continuous effect on the latent amount of agreement you have. And then because we're forcing you to choose like a specific strongly agree, neither agree, disagree, etc., because we're forcing you to choose one of those categories, that we are then kind of observing as your latent agreement increases, when do you kind of like hit the threshold for responding to each of these ordered categories. And the reason I talk about this is because it can actually help us provide a second extension of beta regression that sort of helps figure out some of the problems that we had with Zoib. So remember, beta regression has the problem that it can't model exact zeros and ones. And if you've ever done any behavioral research, you know that when we have values like proportions or, percentage correct or something like that, we often have exact zeros and ones. So Zoib basically tries to use mixture models in order to overcome that problem. We model everything as a mixture of a 0 component, a 1 component, and a between 0 and 1 component. However, that had some issues because each of those components were essentially modeled independently, which could lead to some really counterintuitive results. So instead, something that only recently was developed is ordered beta regression. So in ordered beta regression, we essentially have still 3 components, but those components are modeled in the same way that our cumulative logit models were modeled. Basically, we have a continuous latent distribution, and we have one cut point below which you would be a 0, and another cut point above which you would be a 1. And then everything between is just your typical beta regression. So again, what we're doing, instead of assuming these kind of discrete mixture components like we would in Zoib, is we're assuming that there's a latent continuous variable, and we're modeling the impact of various predictors on that latent continuous variable. Now, of course, we also model at least 2 cut points, below which you're 0 and above which you're 1. Now, this basically gets rid of the issues that we were having with Zoid. Because we're modeling things as that latent variable, when we increase your latent variable, the predictor is always going to increase your predicted latent score. And where that lands you will determine if you're a 0, a between 0 and 1, or a 1. Essentially, we're creating a regression model where our latent continuous value that we're assuming exists is modeled kind of like a regular regression. All right, so we've talked about a few maybe less traditional extensions to the generalized linear model framework that help us actually fit situations that we really have and make some of our simpler models a little more fitted to the situation that we need. All right, that's all I have for you. I will see you next time.